Hello. My name is Dr. Aaron Lee. I'm the professor for this course, and welcome to Physics 105, Classical Mechanics, or Analytical Mechanics. So for those watching, this course is usually taken in the spring of your sophomore year here. So it's assumed at this point that you've completed the intro sequence of physics, modern physics, as well as the first 3 semesters of calculus. Differential equations is nice, but it's usually assumed that you're taking it concurrently while you take this course. This course is meant to be a 1-semester version of the subject, drawing from the usual variety of texts. And the topics that I choose hop around kind of what's emphasized in different textbooks. Some of it kind of delves back a little bit into the intro sequence that I think students could benefit from seeing a review of. So ultimately, these are topics that I find most relevant for students here at their current stage in the curriculum. This is viewed often as kind of an intro to the upper levels here. In the plan that I'm structuring it this year as a flipped class, where these lectures will be broken up into modules, which each module will kind of focus on a particular topic or idea, and that will serve as the content of the course. It will be me lecturing, me doing derivations with simple examples, while the in-person meetings, for those of you who will be meeting with me in person, will be focusing on doing more examples, more complicated examples, and then group work problem solving. And since I'm breaking it up not based on lecture, but kind of based on topic. So since these are kind of modularized by topic, it might be expected that you have to view a couple of these for a given class. Or it might be that we watch one of them and then spend the entire week doing examples on those sorts of ideas, depending on what's being covered in that module. And since you can come back and watch these videos again and at your own pace, I won't worry too much about the length, though I will try to not make them too unwieldy. I'll aim for an on average 30 minutes, but I know I'm going to fail on occasion with that. And apologies for I inevitably stutter a little bit, and I might make a mistake or a whoops. So apologies for that. So let me start by, can we write down just what our ultimate goal is? Ultimate goal. I guess with the recording, you're going to see the side of my head a lot as I write. That's okay. What is the ultimate goal for a course like this? Ultimately, I'm going to write down our goal in 2 different ways, and then we're going to kind of build it up in sophistication as the motivation of this lecture. So the ultimate goal I want to say for classical mechanics is that we want to describe how macroscopic objects behave. So to describe how macroscopic objects behave. Which is a pretty vague statement, admittedly. We can build upon that a little bit and say, okay, what really do I mean in a kind of mathematical course like classical mechanics is that I ultimately want to derive equations of motion. Derive equations of motion, which these equations of motion we will see are going to be differential equations. That, when solved, determine the motion of macroscopic objects. That, when solved, determine the motion of macroscopic objects. Even that, I think, needs a little bit of clarification. But that ultimately is what we're aiming for to do in a course like this, classical mechanics. Classical mechanics as a subject, right, really focuses on understanding the set of rules that can be used to describe a system. On one end, what do I mean by that? One end, I might mean that you are trying to figure out the rules that describe a particular kind of motion, which I might call the equations of motion. For example, which laws of motion dictate how a box moves down a ramp? Are those the same or different equations of motion that dictate how the Earth moves around the sun once every 365 and a quarter days? These are, coming up with a set of differential equations or rules that then, when solved, tell us the subsequent motion into the future of that object. Turns out into the past as well. We'll get back to that. Is ultimately kind of at the heart of what we're trying to do. On another hand, classical mechanics allows us to ask about what rules for the allowable laws are allowed. Can we say something about the grand framework of dynamical laws of motion overall, and what makes a dynamical law of motion versus something else? And that's something that we've never seen before until a course like this. We can start to ask ourselves about what allowable laws are out there and what allows nature to say that one thing is a dynamical law and what one thing is not a dynamical law. Now that's a little abstract, so here's an idea. Here's a simple idea to kind of motivate this. Let's take that box moving down a smooth ramp. So here's a box, and we know at some future time it ends up here at the end. This might be the start. And it's released from rest, frictionless surface, blah, blah, blah. Now we know from our study of physics in the past of what this motion looks like. It will start to accelerate and its velocity will be slow and speed up and speed up and speed up. And by the time it reaches the bottom of the ramp, it'll be moving fairly quickly. However, I could say, what prevents me from saying that the answer should be that it immediately starts careening down the ramp, but then slows down as it gets towards the bottom? That's another way where it could start at the top and end up at the bottom. What's to stop me from saying that if I release the box from rest, it initially moves upward a little bit, turns around, and then eventually makes its way towards the bottom of the ramp? Or finally, what's to say that if I release a box from rest on the top of the ramp, that it doesn't immediately then first go horizontally off the ramp until it is vertically above its end position and then goes vertically down and ends up at the bottom of the ramp? These are all various ways the box can start from rest at the top of the ramp and end up at the bottom of the ramp. But clearly only one of those actually happen. Why? We can start to ask ourselves. Why is, of all these, well in this case only 4 possibilities I've given you, of infinite possibilities really that I could have written down, why is what I've drawn with the black arrows the one that actually happens? That's what I mean when we can ask ourselves what allows dynamical laws to be dynamical laws. Why do things like energy, momentum, angular momentum, if I want to call them those words, end up being conserved quantities versus, say, just velocity? Why is velocity not a conserved quantity, but momentum, which is mass times velocity, can be conserved in particular contexts? This alone, hopefully, is on its own a strong motivation for why we should study classical mechanics. But furthermore, classical mechanics is at the heart, still at the heart, of so many processes that we experience here on Earth. While quantum mechanics and relativity are scientific models of reality that we believe give improved visions of how nature works, the realm of classical mechanics, namely Newton's laws of motion, still provide an exceptionally accurate view of the world. I do not need to invoke the full machinery of quantum mechanics to study how a box moves down a ramp. I could use quantum mechanics to study this motion and I would get the right answer, but I would have to do an absurd number of complicated mathematical steps in order to go from studying a box just moving down a ramp, where I would get the same exact answer, more or less. I'm just going to say, I would get the same exact answer to any sort of experimentally verifiable measure using Newton's laws of motion in this case. Nonetheless, classical mechanics still is an approximation. We know there are cases where classical mechanics fails. If you're moving close to the speed of light, Newtonian mechanics starts to break down. If you happen to be hanging out outside the vicinity of a neutron star or black hole, sometimes things don't even work. And people have seen for centuries even that even when you're not even near those absurd kind of extreme limits, sometimes there are deviations from what you would predict with Newtonian mechanics. The orbit of Mercury is kind of one famous example. As Mercury goes around the sun, its orbit precesses at a rate that Newtonian mechanics could not calculate. Or rather, it calculates a different number than what was being observed. And it wasn't until actually that was one of the first tests of Einstein's general theory of relativity. When he came up with his general theory of relativity, one of his first things he did was use it to predict the precession of Mercury and got the answer exactly right. So it was the first kind of feather in his cap that he could justify motions that were observed and measured, but Newtonian mechanics was not getting correct. Okay, so then why study classical mechanics at all? Right, if it's not the truest representation of reality. Well, again, it still gives very, very accurate results when you know your limits. If you know that you're working in the classical regime, why not use Newtonian physics, which tends to be much less complicated than higher order models of nature, when it gets you the same answer? It also gives us a playground that has a little bit more intuition built into it, where I can imagine boxes moving down ramps and pendulums swinging, where I have a hard time imagining what it means for an electron to be in some sort of orbit around a nucleus, where it can be there and it's not there, and there's quantum uncertainty and all that nonsense, or relativity, where everyone's clock is ticking at a different rate and everyone's ruler is a different length. So by focusing on these bigger ideas in the classical regime, that allows us to build some intuition that can then be applied to these larger branches of physics. Bigger ideas like conservation laws and the action principle can be much more easily understood in the classical regime, but apply beyond Newtonian physics. The action principle we will see, or well, I guess I just have to tell you, the action principle, which we'll see at the end of the semester, but deriving dynamical laws through the action principle actually is the best way we have of describing new laws of nature. So let us use that as well as a motivation in studying Newtonian physics. But I'll give you, again, a little bit more context into kind of how this fits into the bigger scheme of physics. This is a figure taken from a new book by Kip Thorne and Roger Blandford. Apologies, I did not ask their permission to use this. But it kind of shows you kind of where this class fits in terms of its applicability, though again, I argue that by developing the intuition for bigger ideas like action principles and conservation laws, which do apply to the other realms of physics, Newtonian physics actually holds a pretty solid location in the development of our understanding of physics. So here we are down here in Newtonian physics, and it's kind of in the classical limit, right? So you can imagine everything over on this side is kind of quantum mechanic realm, and then this is the classical realm. So we're not dealing with uncertainties that come with when you try to deal with things on the very small or the very dense. And so that kind of gets you from left to right, and then from top to bottom is kind of dealing with if you think of this in terms of Einsteinian space-time, that you're not dealing with fields or things moving at or close to the speed of light, which is kind of the realm of kind of special relativity or quantum field theory. And you're also not dealing with hanging out near things that, to use gravity as an example, where distortions in space-time are so extreme that you really have strong deviations from good old standard Euclidean geometry, for example, which is kind of the realm of general relativity and kind of more general quantum field theory. And so we'll be working kind of in the limits, at these low speeds. You might think of that as velocities are much, much less than c. That'll be one assumption we make in this course. The classical limit might be that kind of sizes of objects that we're dealing with are going to always be assumed to be much, much greater than, say, the de Broglie wavelength of the object. So the de Broglie wavelength is defined as Planck's constant, and for a massive particle divided by m times its velocity. It's kind of the characteristic size of the wave function for something in the, so I kind of like to think of it as an order of magnitude estimate of when does quantum mechanics matter. If you're dealing with length scales that are comparable to an object's de Broglie wavelength, you probably have to treat the thing quantum mechanically than as a true just kind of solid particle or object. So we're always going to be working in limits where we're kind of bigger than de Broglie wavelengths. We're not dealing with the quantum mechanical realm. We're not going to be dealing with things that are moving super, super fast or at the speed of light. Kind of something that's kind of built into this also is that we'll be dealing with macroscopic objects, which really what I mean by macroscopic objects is that we'll be dealing with things that have non-zero mass. We won't be dealing with fields or photons or anything like that. And then the general relativistic content is that we're not dealing with distortions in space-time that are so extreme that we have to deal with, extreme curvatures, right? You might define that just as an order of magnitude as I'm dealing with masses that are less than about the speed of light squared over, times the size of the object over g. Again, don't worry about where that comes from. But, that things, around these kind of Schwarzschild masses, right? It tends to be when distortions in space-time get very extreme and you need to think about things general relativistically compared to classically. So we're going to work kind of in the limits of things that are bigger, so we're not dealing with quantum mechanics, not moving too fast, and are not absurdly massive that we have to deal with with local distortions in space-time. And here, what this one is, another way of thinking about what these mean is that by saying that L is much, much greater than the de Broglie wavelength, what that is telling me is that there is no quantum mechanics, no uncertainties that I have to deal with, so I can say that I can exactly know positions, velocities, energies, that sort of stuff. Speed's much, much less than the speed of light, so no relativity. Another thing I might think of in this case is that I can say that there's an absolute time. Absolute time. Right, but I can, as Newton believed, think of there being some big grandfather clock somewhere in the cosmos where all of us can sync our watches to, and we don't have to worry about relativistic times and how we measure events in space-time. And then with masses kind of being less than c squared L over g, where this is saying no general relativity. And you can think of this also as saying is that I'm working in the limit of absolute space. I'm not dealing with localized curvature. So really what I mean by this is that Euclidean geometry is going to be perfectly fine. I don't have to go into differential geometry and Riemann tensors and all that fun stuff. So, under those motivations, let's see if we can reframe our ultimate goal a little bit in this context. Right? So then I might say, coming back to our ultimate goal, is that I want to describe the motion of massive objects and again, what do I mean by massive? Objects with non-zero mass as a function of time. And this might be some sort of vector expression for multiple dimensions, but I want to describe it as a function of this kind of universal time as it moves through space. Or similarly, I want to derive equations of motion, UM, that when solved give a unique solution. Now I'll call that solution R with a little arrow as a function of time. Again, some vector expression that might tell me positions as a function of time, which can be multidimensional, for a given set of initial conditions. Tell me the equations of motion, which are going to be differential equations, things that need to be integrated and solved. Integration, as you know, often introduces constants of integration, which can be evaluated with your initial conditions to give you a unique equation or solution, or in the case where things had to be done numerically, kind of a unique down to numerical error solution of the trajectory of some sort of system, which can be an object or many objects or whatnot. That is really the goal of what we're trying to do here. Perhaps unsurprisingly, this course deals with mapping natural processes in the physical world to the language of mathematics. Mathematics is, in many cases, I would say, the most precise of all the languages out there, right? Because it's unforgiving to sloppy interpretations. For mathematical things to work, right? We've all taken calculus, but if you were a math major, you take a real analysis course in your upper level math courses, which is all about just how calculus works. I take 3/4 of this course at Northwestern, which is just delving into the details of why calculus actually works. And these sort of things rely on that mathematics requires very precise definitions, which through logical mathematical reasoning can then be used to derive equations or solutions that then have very precise interpretations. Ill-defined definitions lead to ill-defined relationships. Sometimes you call that common sense. Right? Common sense, you usually have a good feel for how things should, how some definitions translate to some effects or some processes result in some sort of outcome. But sometimes you get led astray, and that's just maybe because your definitions are a little too vague or a little too imprecise. Physics tries to be more exact, right, through the language of mathematics, right? So physics is an exact science in a sense that correct mathematical reasoning allows you to not only say something quantitative about what's going on, but qualitative as well. I realize I flipped those. Let me try that again. It allows you to say something not only qualitative, but quantitative as well. You get both, even when the quantitative relationships themselves are statistical in nature. So perhaps unsurprisingly, this is a somewhat math-heavy course. But that's another motivation for why I chose to record these videos, because derivations, examples can be revisited because you have the pause button or the space bar. You possess the power to pause me, quite unlike in class where no one rarely has the power to stop my inertia as I'm talking. And that said, maybe before we get to the closing thoughts for today, I, of course, cannot myself make you masters of this material. You have to practice as well, which is then, of course, why you have various textbooks, right, which you should try to solve problems, related to this material. And then, of course, those of you in the class will be going into doing lots and lots of examples in class about these ideas. But if you're taking this as a part of a class, I would still say do take notes. Don't just passively listen to me. Take notes on what I'm saying, because we'll probably spend time in class going over your notes and allowing you the opportunity to ask questions about the material before we get into the examples. And of course, then seek out the textbook end of chapter problems and try some out for yourself. Okay. I realize I forgot a word here. Motion of massive what? Massive, I guess we could say particles as a function of time. And I make that because despite the intro sequence, rarely do we deal with individual objects, right? We're familiar with treating things as point particles. And perhaps it was said more directly in your intro sequence, or perhaps it was not. You know, there are assumptions going into the fact that I can, say, treat this apple as a point particle and still get the exact right answer in terms of its motion as I throw it up into the air and it falls back down to me. While in reality, this thing is made up of trillions and trillions and trillions of atoms. Even the simplest cell, simplest human cell in my body is made up of millions and millions of subatomic particles. So nothing really is a point particle, yet I can talk again about the apple's motion with great accuracy, even though as if it was a single particle with all of its mass located at, I don't know, this thing I might call the center of mass of the object. I can approximate the entire Earth, including all its inhabitants, as it careens around the sun at 30 kilometers per second as a point particle. But ultimately, what we are ultimately trying to do is we are trying to describe, in a class like this, where we're trying to get a little bit more sophistication beyond what we had in the intro sequence, we're trying to describe the dynamical motion of systems of particles. So I might, again, do another version of this goal, right? To describe the evolution of a system, which a system I might call a collection of particles, waves, fields, etc. Right? It can be a whole variety of things as a function of time. And that might be, I'm trying to describe this apple's motion, which itself is made up of many, many, many particles as a function of time. It could be that where, in this case, this is more of a rigid, solid object, where the relative positions of all the atoms in the apple aren't really changing as I throw it up and down into the air. If you do want to take that into account, right, then you're including stresses and distortions on the object. But if we treat it as a rigid object, all the relative motions between the particles are very small. So relative motion we have to think about a little bit too. But it could also be that I want to describe as my system the entire solar system, where there are planets and moons and they're all going around the sun, but they're all also moving relative to one another. As the moon goes around the Earth, there's relative motion between the Earth and the moon as they both go around the sun. When can I treat Earth plus moon as a point particle? When can I not? And so we want to try to delve into a little bit more about what we mean by the evolution of systems, where the internal motion of the systems could be rigid, kind of like the solid apple, or it could be dynamical, where there's relative motion inside of it. And so then we do this by determining dynamical laws. So to determine dynamical laws, to describe the evolution of a system. And now let me introduce something new, that without kind of quantum mechanical uncertainty, without that having to do with quantum mechanical uncertainty, dynamical laws in classical mechanics must be what I'm going to call reversible. Or another word that I could use instead is they must be deterministic. And that means that these laws can be something that can be solved kind of backwards and forwards. And they give you perfectly valid representations of nature. Laplace was a big pioneer of this idea. And really what all it's saying is that the universe today is a result of the universe in the past. Tell me what the universe was yesterday with my dynamical laws of motion. I'll tell you what the universe will be like tomorrow, or today rather. The universe of the future is a result of the universe today, right? If I knew all the positions, velocities of particles, and the forces acting upon them, and the dynamical laws of motion that apply, I could play the movie forward and turns out as far as I want into the future. Or I could play the movie backwards as far back into the past as I wanted as well. That's what we mean by reversible. Dynamical laws are reversible. Throw the apple into the air and you can figure out the trajectory and the path of the apple as it moves from one hand to the next. But then I could play the movie backwards where the apple kind of moves in the reverse direction as well. And if I didn't tell you which way was forwards and which way was backwards, you actually might have a hard time telling me which is which. Said another way, I could throw this apple into the air. Then I could throw a minus sign in front of all the velocities and play the movie again, and the apple would trace out the exact same path, but in reverse, as if I was playing the movie backwards. So, given a past, you can figure out the future, right? Given a current point in the present, I can also tell you something about where I came from, what my past was. Now, this is not to be confused with irreversible processes. So an irreversible process is something where time is always moving forward. Think of an example of, I could take this apple, I could push it across a rough table, it would eventually come to rest. If I played the movie backwards, then it would look like the apple is moving backwards and speeding up as it returned back to my hand. But that's me playing the movie backwards. That is different than me saying that I take an apple and I throw it one way across a rough table. It comes to rest eventually. But then if I went to that apple now at rest and push it in the exact opposite direction, of course we would not expect it to speed up as it returned back to the point where it started with. Right? It would slow down in both contexts, right? That's because friction, right, is kind of an example of an irreversible process. You don't get the same thing back by going in the opposite direction. Unlike gravity, where going up I slow down and then coming back down I speed up, and kind of what I lose I gain back. You might think that sounds like a conservation law. It is, but I get ahead of myself. So irreversible process. Most of nature is sets of complex irreversible processes, where again time is always moving forward, and you're not the egg is not reshaping itself after it's cracked in the pan. Your dorm room is not cleaning itself up miraculously. You have to put in effort to actually clean up your dorm room. You have to invest energy to clean up your dorm room. This gets us a little into the weeds, but when you take statistical mechanics and thermodynamics, you talk about this thing called entropy, and how entropy always tends to increase with time, this active disorder. And in many ways, you could call that the fact that since most processes in nature are irreversible processes, kind of marching, as time marches forward, they march in one particular direction, you can actually use that to define the arrow of time. Which way does time tick, right? It ticks in the direction towards whatever direction processes are taking towards their irreversible endings. But again, let's leave that for another class. Or you can ask me about it in office hours or something. But dynamical laws must be reversible, which means if I play the movie backwards, that must also be an appropriate solution to the dynamical laws of motion. Which again is different than just trying to do the thing while time moves forward in reverse. Let me use a kind of a simple example that I really like from Leonard Suskind's book, The Theoretical Minimum. He's a physicist down at Stanford, where he gives an example of kind of a simple stroboscopic version of how you can derive dynamical laws. So let me take a system, which I'm going to represent by this comically large quarter, where there are two possible states that I can find the system in. I either find the system as heads, or I find the system as tails. And those are the only two possible states or configurations that are possible for this system. And I'm not worried about how it becomes heads versus tails, Again, this is kind of a stroboscopic version where it's either heads or it's either tails. And if it changes from one to the other, there must be some sort of dynamical law that tells me how that happens. But again, I'm not worried about kind of how this exists in a kind of universe where the coin can flip or something like that. A dynamical law must be able to tell us, and I'll represent this by drawing arrows, that if I tell you what the system currently is, either heads or tails, what is the future of that system? Is it going to change or stay tails, or who knows? And I also must be able to go back in time and say, okay, if I find myself in a state of heads today, what does that mean about where I came from? Was I heads in the past? Was I tails in the past? So kind of the simplest version might be something like this. This might be an example of a dynamical law. If you're heads to start with, in the future, you become heads. Then if you're heads again, in the future, you become heads. Essentially, you always stay. If you're heads, you're always heads. If you're tails, you're always tails. And notice this tells me how things evolve both forwards and backwards, right? If I find myself in heads, I can ask, where did I come from? And I can follow the arrow backwards. I came from being heads. If I find myself being tails, I came from being tails. It's a pretty simple dynamical law. Essentially, your state does not change. This could also be a dynamical law. Right? Heads or tails. If I'm heads, I become tails. If I'm tails, I become heads. If I currently find myself as heads, tomorrow I might find myself as tails. If I currently find myself as heads, in the past I was tails. I can go backwards and forwards in time without ambiguity. This is a dynamical law, right? It's telling me both my past and my future. It's reversible in that both directions don't have any ambiguity of how my system evolves. It's like let's upgrade to 3 states. Make it a little bit more interesting. So maybe it's heads, tails, and I don't know, Mario. So one example of this could be if you're heads, you become tails. If you're tails, you become Mario. If you're Mario, you become heads. That would be an example of a dynamical law. Right? If I currently find myself in tails, I'm going to become Mario with no ambiguity. I came from being heads with no ambiguity. And then I can do the same thing for Mario, and then I can do the same thing for heads, of kind of where I came from and where I'm going. Heads, tails, Mario. Could be that Mario stays Mario, but heads and tails kind of swap back and forth. Maybe that's also a dynamical law, because again, there's no ambiguity as I go from one state into the future and one state into the past. Here's an example of something that would not be a dynamical law. And you're encouraged to maybe pause and think about why this is the case before I say the answer. Right? Heads becomes tails, tails becomes Mario, but then Mario becomes tails. That is not a dynamical law. Even though there's no ambiguity about the future. If I start as heads, I know I'm going to become tails with no ambiguity. If I start as tails, I'm going to become Mario with no ambiguity. If I start as Mario, I become tails with no ambiguity. But that's not the case when I look into the past. Mario, there's no ambiguity, right? If you find yourself Mario, you came from being tails. Heads has no past. There is no past to heads. So how did you get to heads in the first place? Could be a question someone might ask. Right? Heads has no past. And then tails has the issue where it has 2 possibilities for its past. A heads can become tails, and a Mario can become tails. So there's ambiguity in terms of if I give them my current state today, where did I come from? That's not deterministic, not reversible. In this case, even though there's no ambiguity about the future, there is ambiguity about the past for some of these states. So I would not call that a dynamical law. And then last, let's suppose I have a state that has a system that has three possible states, which I will label as 1, 2, 3, 4, 5, 6. Oops. Maybe it's the case that 1 becomes 1, 2 becomes 3, 3 becomes 2, and then 4 becomes 6, 6 becomes 5, and 5 becomes 4. This is a system, right? In this case, I would say this is a system with 6 states. It is a dynamical law based on the arrows, right? There's no ambiguity. If I find myself as 2, I know I came from 3 and I'm going to become 3. If I find myself as 6, I know I'm going to become 5, but I came from 4. But this particular dynamical law has actually some interesting information encoded in it. In that if you know about which cycle you're in, you know that of the in this case only 6 possibilities that there are configurations or states that you can and cannot access depending on some sort of quantity that determines which of these cycles you're in. Or I might even say, I could look at this 1 and I could paint it red, or I can use that to label this particular cycle. I could look at 2 or 3 and I could call that a cycle and I'll label it green. And this one I can label cycle blue. And I could define some quantity. So there are kind of 3 cycles, which I've labeled by maybe some quantity Q, which I'm calling kind of color in this case. I could have called it by something else. I could have said that state 1 has a value of Q equal to 3 joules. The greens, state 2 and 3, have a value of this quantity Q, which is maybe 5 joules. And then the states that are blue might have this quantity Q, which might be 0 joules. And this quantity Q, which sounds a lot like energy, maybe I'll just call it energy to pull a word out of the air, is a quantity that is conserved amongst that particular cycle, right? In the case of colors, if you're green, you're always green, or your energy it might be always equal to a certain value. If you're blue, you're always blue, or maybe this quantity I'll call momentum is something that always has the same value. Well, those cycles sound a lot like conservation laws, or just as or a lot like conservation. And so the cycle, right, a cycle, which might be thought of as a subset of states, determine the value of some conserved quantity. And look at that. Something that might seem magical in the intro physics sequence kind of is emerging kind of naturally in this idea of these kind of stroboscopic 6 states, heads, tails, or sides of a die, or that sort of thing. And this easily then extends when there are seemingly infinite numbers of states which can have multiple objects, where you have 2 coins, where you might have heads, 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 tails, tails, heads, and tails, tails. You could have some sort of dynamical law that goes between those 4 possible states, for example. You're labeling the system by its possible configurations, and within those configurations, interesting properties might emerge. In this case, I might call it a conservation law. So that's saying something, again, if I had rules of when that can and cannot happen, that's saying something about what dynamical laws are and are not allowed. This might seem abstract, because it is. But it is at the heart of what we're trying to do here, of trying to add a little bit more sophistication towards how we build an understanding of not only how can we derive mathematically laws of nature, which again will be another component of this course, right? Given it's so math heavy, we'll get very comfortable with those sorts of mathematical skills, as well as trying to say something a little bit more meaningful about where these laws of motion and laws of nature come from.